All right, good evening, everyone. Just wanted to provide you all with a demo, giving you an example of sort of an approximation of creating a sampling distribution. We talked about sampling distributions in class, but this is just such an important concept. It can be kind of difficult to wrap your mind around in the abstract, and so what I wanted to do with this video is just walk you through what it might look like if we were to create a sampling distribution with a relatively large set of scores that we might generate in SPSS. And so, again, when we're talking about sampling distributions, the sampling distribution that we had focused on is the distribution of sample means. If you recall, distribution of sample means is referring to the distribution of means that we would create from all possible random samples of a given size that could be pulled from a population. And we remember that we had talked about, like, if we were to do this, this distribution of sample means has certain properties that become helpful for us in terms of statistics. If we move forward, just as a refresher, remember that the distribution of sample means has a specific shape. And remember that the distribution of sample means the distribution approaches a normal curve under two conditions. One, if the whatever variable that we're looking at has a normal distribution in the population. So if we're looking at something like height, different personality characteristics, these types of things that we would expect to have a normal distribution in the population, then the distribution of sample means is going to approach normality very quickly. Okay, but sometimes variables of interest probably don't have a normal distribution in the population. Sometimes we're going to be looking at things like aggression or substance use or other types of variables that are probably going to have a pretty skewed distribution in our target population. Here, the distribution of sample means still approximates a normal distribution as long as we have samples of around 30 or more. That sampling distribution starts to approach normality very quickly. So we had talked about the shape of the sampling distribution, and then we also talked about central tendency. Recall that the expected value of the mean, this is the mean of your distribution of sample means. So the mean of all possible samples of a given size is going to be equal to the population mean. So in the example that we provided in lecture, we've got height of adults, let's say in the US. If we were to go through and collect all possible samples of 100 with replacement from the US population, we would see that that distribution of sample means would approach normality very quickly, and we would also see that the mean of that distribution would be the exact same value as the population mean. Okay, and then we also talked about variability. Remember, our variability of our distribution of sample means is our standard error, and a standard error is literally the standard deviation of the distribution of sample means. Conceptually, we can think about standard error in a couple of different ways. One, thinking about an index of how much difference we would expect from one replication sample to the next. So as I go through and I randomly select adults from the US population, how much would I expect their average height to jump from replication to replication? We can think of standard error in that way. We can also think of standard error, and this is useful for our statistical inferences in terms of how precise our sample is going to be. How well is our given sample of a given size going to approximate the actual population mean, or we can think about this on average, how much difference we would expect from any randomly selected sample of 100, how far we would expect that to deviate from the true population mean. If you recall here in our sample, we have standard deviation of height is 6 inches in the population, and so our standard error, the mean, is going to be our population standard deviation divided by the square root of the sample size. So if we take 6 divided by the square root of 100, which is 10, it's going to give us a standard error of 0.6 inches. So in this example, we would expect on average that any randomly selected sample is going to deviate on average about a little over a half of an inch from the true population mean. And so in this case, we're talking about something that's very precise. Okay, so this is well and good in theory, but it can be difficult to visualize. So what I want to do is I want to calculate just with some randomly generated data, a sampling distribution. So what I'm going to do, hoping my computer doesn't freeze up, is I'm going to create a population of scores. Okay, and I'm going to put this population at 1,000. So I'm going to take these scores, I'm going to open up a new SPSS file, and I'm going to paste these in. And this is going to be my population. Oops. Okay, and so this is my population of individuals. This just represents all 1,000 people in my population of interest. Okay. Now what I'm going to do is I'm going to go through and I'm going to compute a variable. I'm going to call this variable normal. And what I'm going to do is I'm going to tell SPSS to create some random numbers. And specifically I want those random numbers to follow a normal distribution. Okay, and what SPSS is going to do is it's going to generate 1,000 random values, and I can tell it I want that set of values, I want to have a mean of about 50 and a standard deviation of 10. Okay, and so what SPSS is going to do, it's going to create a new variable that follows a normal distribution with mean of 50, standard deviation of 10. Hit OK, and here are my scores. Now, for the purposes of this demonstration, I kind of want, so I generated decimal places on this, which I don't necessarily want. So I'm going to copy these and just get rid of that decimal place. I think I can do that here. If I format my cells, say this is a number. Okay. I think what I should get here, now values without a decimal place. Perfect. Okay, so I'll get rid of that. Call this normal. No decimal places. Okay, so what I have now is I have a population of 1,000 scores, all right, and this is everybody in the universe who I'm interested in. And we should, if SPSS has done this correctly, find that my normal variable here should have a mean of 50, a standard deviation of about 10, with very little skew or kurtosis. Okay, and if we take a look at that, we see that, yep, that's what we've got. We've got a variable with a mean very close to 50, a standard deviation very close to 10, and very little skew or kurtosis. And if we were to go through and look at this variable graphically, we would say that we've got a very nice distribution. So this is my population of 1,000 scores. Okay. So what I want to do now is I want to go through and I want to, actually here I'll go paste that into a syntax file. And so what I want to do is I want now SPSS of that sample of 1,000, I want it to randomly select samples of 30. And so I'm going to go down here to select cases. I'm going to tell SPSS to select a random sample, exactly 30 cases from the 1,000 cases I have in my population. So what this is going to do is it's going to randomly select a sample of 30 cases. And so I'm going to hit continue, and then I'll hit paste, and paste this into my data set. Okay, and so SPSS here is going to select me a random sample of 30 cases, and then it's going to give me the mean of those 30 cases. So if I go through and I select this, okay, what it's done is it's gone through the program. We've got this filter, so we've got here's a case, here's a case. So SPSS has randomly gone through and selected 30 cases from my population of 1,000. And then what it did is it calculated the average of that sample of 30. And so it looks like my sample of 30 here has a mean of about 48.5. Okay, and so what I'm going to do is I'm going to take that mean of 48.5 and drop it right here. And this is going to be my sampling distribution. So I'm going to call this sampling distribution normal with 30 cases. Okay, and so we see that of these 30 cases have a mean of 48.3, a standard deviation of 11, getting close to 12, but again, skew and kurtosis isn't too bad. But what I can do, because I have this as a syntax file, I can just run this again. And what SPSS is going to do now is it's going to generate a new sample of 30, and we see this time we got a mean of 46.3, so that's a little bit lower. I'm going to drop that in right here. Okay. Now what we could do is we could do this again and 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 again, and do this over and over and over again. And so what I've got here, just because you don't want to watch me paste stuff into a file, I did that for 100 times. So what I did here is generate random samples of 30 with a randomly generated normal variable here over 100 different sets, generated 100 sets of sample size 30 and recorded their means. Okay, and so if we go through and we take a look at in this set, I'm going to ask for a histogram and take a look at my normal variable again, just so we can refresh our minds on that. Okay, this is my normal variable. Okay, in this situation, it's got a mean of 50, standard deviation very close to 10. This is all 1,000 scores. What I'm going to do now is I'm going to go through and I'm going to look at my distribution of the 100 random sets of my sampling distribution for my 100 random sets of 30, and go through and take a look, and we see that my population distribution has a mean of 50.16. See that my sampling distribution has a mean, or my expected value of the mean is 50.25. So we're very, very close. Okay. We also see that the standard deviation of my population here is 9.623. But if we go equals 9.623 divided by the square root of our sample size 30, we would expect that our standard error for this population, given sample size 30, to be about 1.76. And if we go down and take a look at our standard deviation of our distribution of sample means, we see that it's very, very close. It's 1.8. And so remember that this is just a small selection, right? This is only a random, a set of 100 samples, not all possible samples of 30 that could be drawn from the 1,000 cases. And also remember that these samples are drawn without replacement, where mathematically we would be checking this in terms of drawing random samples with replacement. But still, even with this very simple set, we can see that the expected value of our mean, or our mean of our distribution of sample means, is nearly identical to our actual population mean, and the standard error is almost exactly what we would expect it would be given a population standard deviation of 0.962. And we can see as we go through and take a look. So basically our standard error is saying we would expect any two randomly selected samples to be just a little bit under 2 points away from one another. And as we go through and we take a look, that's what we're seeing. We're seeing things jump around. Now, that's not to say that we can't have some samples that end up being quite low, some being quite high, but basically my distribution of sample means here is turning out basically as I would expect based on math here. Okay, so now another thing we could do, so this is fine for a normal variable. Let's say though that we don't have a normal variable. Let's say we have a variable that's got a lot of skew to it. Okay, what I'm going to do now is I'm going to go through and compute a new variable, and this variable I'm going to call skew. And my skewed variable that I'm going to have SPSS generate for me, I'm going to have it generate a random set of scores that follow chi-square distribution. Now, chi-square distribution is skewed particularly with only 1 degree of freedom. Okay, so this new skew variable is going to be randomly set of values derived from a chi-square distribution with 1 degree of freedom. If I generate that, here's my new set of randomly generated variables. And if we go through and we take a look at our descriptives here for our skew variable, now this is a whole new distribution. We hit OK. Whoops. Analyze. Ask for skew and kurtosis. Okay. We see that our population, right, of our new variable skew, we have 1,000 values, but we see that this distribution has a mean of about 1 and a standard deviation of 1.3-ish, but we'll see that we've got a fair amount of skew and a good amount of kurtosis here. And if we go through and take a look at what this looks like, you can say that that variable is nasty, right? That's definitely not normal. But remember that as we would expect the distribution of sample means for this variable to start approaching normality very quickly if we've got reasonably large samples, right? So what we're going to do is we're going to go through and have SPSS again select random cases. But what I want to do now is select a random set of 100 cases. So we're going to have samples of 100 from our 1,000 scores in our population. I'm going to paste this into my syntax file. Okay. So what this new command is going to do is instead of samples of 30, it's going to select samples of 100. And what we're going to have it do for us then is after each draw, it's going to give us the descriptives for our skew variable. Okay, so we're going to highlight this, run, and we see that our first sample of 100 has a mean value of 0.918. And we still have a lot of skew and a lot of kurtosis in that sample, but what we'll do is post this here, and we'll call this sampling distribution skew 100. Whoops, not 1,000, skew 100. Okay, so we can see here that we've got randomly selected samples of 100, and what we've done is from that sample of 100, we've calculated the mean. Okay, and then we go through and we do this again, and we get a new sample of 100, this time with a mean of a little over 1. Okay, and we go through and paste that in, right? So that's 2 samples. And so we do this conceivably again and again and again and again and again and again and again. And if we do this a bunch of times, what we would end up with is a sampling distribution for of samples of 100. And again, what I've done is I've gone through for this set and done this 100 times and pasted those means in for the skewed distribution of sample one of 100. And so if we go through and we take a look at the skewed distribution once again, okay, oops, yes, masking kurtosis, okay. All right, so we've got our skewed distribution here, 1,000 scores in the population. We've got a mean of our skewed variable is 1.02, standard deviation of about 1.3, okay. But if we go through and we take a look not at our population, but our sampling distribution that only has 100 cases, we go through and we take a look, we see that the mean of our sampling distribution almost identical to the mean of the population, even with 100 replications, and then a standard deviation of our sampling distribution that's going to look almost right on top of our standard error. And so if we go through and take a look graphically at our skewed distribution, again, this is gross, right? This isn't anything close to being normal, but if we go through and we take a look at our distribution of sample means of sample size 100, again with only 100 replications, we see that that distribution of sample means starts to approximate normality even after 100 cases. So again, the population distribution looks very different than the distribution of sample means. Our mean of our original population, 1.02, mean of our sampling distribution, 1.02 essentially. And then again, if we take a look at our, we got 1.362 is our standard deviation in the population. Divide that by the square root of 100 people in our sample size of 100. We get a projected, we would expect our standard error to be 0.136. Oops. And if we go down through, we see that our standard deviation of our distribution of sample means, or our standard error, even after 100 draws, is very, very close to what we would expect based on our mathematical theory, 1.36 versus 1.40. Okay. As one last example, let's say we did this same thing, except for instead of samples of 10, or excuse me, samples of 100, we were to select samples of 10 from our skewed variable here. Again, this is going to be below what we would expect to start to get a normal distribution of sample means. But even if we go through with 100 draws, drawing random samples of 10 from that skewed distribution, hit OK, we see that we're still even getting, after 100 draws, and even with a sample of 10, we're still starting to get pretty close. Our expected value of the mean for this distribution, 1.06. Our population mean, 1.02. So we're very, very close here. Again, if we say equals 1.362 is our population standard deviation, divided by square root of 10, we get a standard error with random draws of 10 individuals, a standard error of 4.3, again a lot bigger than our standard error for samples of 100, but we've got a less precise sample. But if we go back through and we take a look, we see we're expecting a standard error of all possible samples, random samples that could be drawn with a replacement, to get a standard deviation of our sampling distribution of 0.431. We've got 0.448. Again, even after 100 draws, it's getting very, very close. Okay, and so again, demonstrating with actual numbers and doing this, hopefully be able to see what's going on with this sampling distribution. So again, as a recap, when we had our normal distribution of randomly generated scores for our population 1,000, we get a mean of the population is 50.16, and when we're drawing random samples of 30, even when we do 100 cases, and not all possible cases, and even when we're drawing randomly without replacement instead of with replacement, our mean of our distribution of sample means very, very close to the population mean, and again, our projected standard error that we calculated from the population based on the population standard deviation, very close to what we would get here. This is our standard error. This is the average amount of any randomly sampled set of 30 scores we would expect to deviate from the mean. Okay, and so this works well for a population with a normal distribution, but even when we take a look at a distribution of scores with a very, very skewed distribution, again, our sample mean in this skewed distribution is going to be a mean of 1.02, and the mean of our distribution of sample means of sample size 100, 1.02 essentially. Again, our standard error or standard deviation of the distribution of sample means almost perfectly on top of what we would expect if we were to calculate the standard error based on our population parameter. And again, the same type of thing. If we drop this down, instead of randomly drawing samples of 100, we're randomly drawing random samples of 10, we still see that the expected value of the mean for the sampling distribution almost perfect on top of what we would expect based on the population distribution. Same thing, if we take the standard deviation divided by the square root of 10, which is our sample size, will give us a standard error, and it comes out almost exactly to this. Okay, so hopefully this helps provide a concrete example of what is going on with this distribution of sample means, how we might go about approximating a generation of a distribution, a sampling distribution, and then giving a better conceptual, more concrete perspective on what's actually going on with these scores. So hope this helps. Let me know if you have questions, and I'll see you all in class on Wednesday. All right, thanks.